Hello everyone, I'm Srikrishna. Shri here and myself will be co-presenting together and we'll share our experience on developing, deploying, operating in-house network switches at massive scale in Meta.
Thanks, Krishna. Hi, I'm Shri. I've been part of the networking industry for over a decade and part of the networking org at Meta for over 4 years. Very excited to bring this talk to you. Here's the outline for the talk. We'll begin by talking about Fboss, Meta's in-house network switching solution. Then we'll go deeper into the Fboss design. Then Krishna comes back and walks us through a case study, and we finally round it off with a section on highlights. Let's get started. Meta has a massive number of servers in the data centers, which means that we need massive number of network switches to interconnect them. When we use third-party vendor devices, one challenge we have is that these are opaque to Meta, which means that if there is an issue, then we have to rely on vendors to debug those issues. That can result into slow turnaround time. The opaqueness of these devices can also mean that it's difficult for us to build tooling and monitoring around them. Put together, this can make it very difficult for us to scale these devices at the rate at which our business requires. Enter Fboss, which stands for Facebook Open Switching System. This is Meta's solution, Meta's software stack for managing network switches in Meta data centers. It comprises of few parts: standard Linux, then these binaries that comprise of Fboss. We'll talk more about it in coming slides. Then the vendor SDK, and finally the vendor ASIC. Vendor ASIC is the piece of hardware that is capable of switching and routing. Finally, Fboss is also in open source. With Fboss, we get better automation, more monitoring and statistics because we understand the network switching software and we develop it. It also means that the bug fixes are faster and so are feature enhancements. And it's not just the code changes that are faster, it's even easier for us to roll those out into production. Finally, having Fboss in the open source means that Meta contributes to moving industry forward in this space. There are a few key ideas underpinning Fboss design. First is that Meta has considerable expertise and learning and tooling in operating large number of server devices. With Fboss, we treat switch like a server and leverage all that expertise as well as tooling. The second idea is to deploy to production early and often, so-called canary devices. The idea there is that if you deploy to production sooner, then you are likely to catch issues a lot sooner, like possibly break few switches often as against breaking all at once. But the critical piece to this is we need ability to upgrade these devices at a very quick cadence, because if you're going to deploy quickly, then you need some ability to deploy those switches faster as well. And this is where onboard comes in. A significant fraction of our devices are rack switches which do not have any redundancy, which means that if you're going to upgrade a software, you cannot take away production traffic as a maintenance window. You instead need ability to upgrade the software on onboard, which is without causing traffic disruption. So this is one of the key pieces of Fboss software. Some examples of Fboss deployment. We had to deploy a new quality of service model, and just contrasting Fboss with vendor devices, where Fboss took us a couple of weeks to deploy this. On vendor devices, third-party switches, it took us several months. Another interesting example is we had a specific use case where we had to dynamically discover IP addresses behind single rack port and associate different quality of service with each of those IP addresses. It was possible for us to envision, implement, and roll this out on Fboss devices in a relatively quick time, something that will be quite impractical for us to do on vendor devices. Let's dive a little deeper into Fboss design. This slide illustrates the Fboss architecture. If you look at the box towards the right top, which is the Fboss agent, this is the binary that uses vendor SDK to program the ASIC, which can do switching and routing. But there are a lot of other components needed as well. For example, the routing daemon. We have support for BGP as well as OpenR. Then there is config management daemon, monitoring, as well as other tools that allow for quick and safe upgrade. If you consider the diagram on the right, it shows a hierarchy of switches. You have servers that connect to rack switches, which in turn connect to fabric switches, spine switches, and fabric aggregators. Fboss as a software and the same software runs on each of these switches in these different roles. But of course, the feature requirement for each of these roles is different. And the way we solve this is by generating config that is unique to each and individual switch. And when the Fboss binaries come up, they read this config and selectively enable and disable different features. In terms of deployment model, we deploy frequently and on a continuous basis. This is how a typical deployment model looks like. If you look at the top box, which is the each Fboss push, we begin with feature development, followed by testing. This is both regression tests as well as tests written for the new features. If all of those look green, then we'll deploy this in production. And this deployment happens very frequently, like several times a day, but at a very small scale. This is what we call as continuous canary. If the continuous canary signals look green, if everything looks great, then it goes to the next stage, which is daily canary. Daily canary is again small set of devices, but bigger than continuous canary, and it picks up changes once a day and deploys it into production. If daily canary passes as well, and if everything looks great there, then we go through what we call as bundle qualification, which is where we choose a new binary that then we are going to roll out to entire production. And that happens gradually in phases as well. If you look at the bottom part of the screen, you see a time window T0 to T1, which is when we are gradually rolling out devices in production with new binary. But code changes keep coming in, There are code changes as well as config changes. As soon as the current push completes at time T1, we start a next push, which will roll out the changes that were integrated between time T0 and T1. So at any point in time, we are only rolling out changes in a relatively small window. This T0 to T1 is typically of the order of weeks, which means that small incremental changes is how we roll out things in production. Sometimes for some features, some non-trivial features, even this can be a little too aggressive in terms of rollout. So we like to pace certain feature rollout even slower than this, depending on the complexity or criticality of the feature or the risk it brings. As an example, let's say in push N, we will only enable this feature, again using the configs we talked about, but we'll enable this feature only on the X% of the fleet. In the subsequent push, say push N+1, we will go to Y%, then to Z%, so on and so forth. On this slide, I took an example of using percentages, but it could be any criteria. It could be a data center, a region, or even a list of specific switches. The tooling that lets you select and enable features is quite flexible in terms of allowing you any scope that you desire to achieve your slow roll. We looked at Fboss and design. In the next section, Krishna will illustrate these ideas with a concrete case study about onboarding new ASIC vendor.
Thank you, Sri, for discussing on how we design and deploy Fboss at scale. Now that we know how Fboss operates, let's understand how we onboard a new silicon vendor into Meta's fleet. The first and foremost goal for Fboss is to have one unified software to run across all vendors. So that motivates us to migrate towards SAI. What is SAI? SAI is a switch abstraction interface. This is open sourced and also is part of Open Compute project. So SAI provides hardware agnostic APIs to define the forwarding elements. So as we migrate towards SAI, we have to rewrite our entire Fboss software so that we can onboard new ASIC vendors. Now that we have migrated towards SAI, we also need to port these hardware test cases. So these tests helps us test our forwarding infra. So these hardware test cases need to be run on both SAI as well as non-SAI platforms. So once we have ported these test cases, then we begin interacting with the vendor. So what is the development model we followed with the vendor? So Fboss is completely open sourced. Any vendor can pick it up, run test cases on them, and then validate their software. So here, when we interacted with the vendor, they built open source from Fboss from scratch. ran test case on them, and made an SDK release. From our side, we took the SDK, integrated with the Fboss, and then we validated more features. We did more development, and we also made, again, contribution to the open source. So how did this help? This helped us to iterate quickly, also catch bugs and fixes easily. So once this, as Sri mentioned, we also rely on onboard heavily for the deployment. So during the new deployment phase, the onboard is not applicable, but as we deployed, a onboard is a must for us. So now that we are complete with the Fboss development, are we there yet? No, because in order to deploy these software, we have to have our push infra, which deploys our software seamlessly. We also need to make sure our monitoring and tools are in place. So the first step is to have enhancements to the push tooling, which has two different stages. The first stage is called qualification, where you will have end-to-end solution testing we run on the new platform. We also need to make sure that this push infra is aware of the new platform, new vendor, new SDK. We also make sure that we run the test case to make sure qualify a production image. So once we qualify a production image, then we are ready to deploy it in the fleet. Now that, how do you know that your device is healthy? So there are enhancements that is required in place for monitoring and tuning as well. These are very specific to vendors, where, for example, like a diaxial client or FPGA utilities, we need to roll them out to make sure that the device is healthy and also help us in debugging. So once these two phases are out, we are ready for mass deployment. So we have several automations in place to mitigate issues, and also we have continuous support from the vendor to ensure that during the initial phase of deployment. This is a quick recap of what we spoke here. The left window indicates how vendor built the Fboss, how they ran the test cases, and how they released the SDK. The right window captures here, like, as Meta, we picked up the SDK, integrated with the Fboss, and this is like a iterative cycle. Once this development is complete, then Meta will run test cases on them, and then make the push tooling enhancements and the monitoring, and then finally we do a mass deployment. That concludes my talk on how we onboard a new ASIC vendor into Meta's fleet. Now I'll hand over to Sri to talk about how we did massive scale brownfield deployment. Thank you.
Thanks, Krishna. So Krishna explained how we had to implement Fboss with a new implementation using Psi API in order to onboard the second ASIC vendor. But now we get into a situation where, while working with the first ASIC vendor, which is massive part of our deployment, we are using one implementation, that is using vendor proprietary API. But while using the second ASIC vendor, we are using a different implementation. And this becomes really hard to maintain and enhance in practice. As a result, we decided to unify our deployment to having single Fboss implementation using the open source Fboss implementation that uses Psi, which is the open source API. So one of the challenges that we realized is that we were looking at a pretty big matrix to deal with. 4 different switch roles, multiple ASICs, and multiple feature sets. So that was a huge matrix for us to take on. What we did is that we identified that a significant number of devices, we have our rack switches, and they also have fewer features as against the rest of the fleet. So we developed for those devices first and started deploying them, while in parallel, we continued our development and eventual rollout for other switch roles. In terms of validation criteria, we use the same hardware tests that Krishna referred to earlier. We have a pretty extensive test coverage. These are like over 1,000 test cases, and each test case exercise is a different aspect of functionality used in production. So the validation criteria or the qualification criteria for us to go from the old implementation to new unified implementation was that if the test case passes with the old implementation, it must pass with the new implementation. And with the comprehensive coverage we have, it gave us a pretty good confidence that we are ready to roll this out into a large-scale existing deployment. Although note that the changes that we had to do going from old to new implementation, those were significant enough that we could not support this over Bamboo, which means we had to do what we call as disruptive upgrades, where you drain the traffic off the switch, upgrade it to new implementation, and then undrain it, that is, put the traffic back in. which also meant that the rollout was even more gradual than it would be otherwise because it had to happen in smaller phases. If you recall, we talked about our continuous deployment process earlier in our talk, and we showed you a diagram showing us different phases where you have feature development, testing, continuous and daily canaries, and eventual rollout. You see it replicated here because while we were transitioning from old implementation to new implementation, which took us significant time, several months, our fleet was split between devices running old implementation and devices running new implementation. We wanted to keep our cadence of continuous deployment on ongoing basis over a few weeks or so, which meant that we had to build a parallel qualification pipeline. So one pipeline for a set of devices still running old implementation and another pipeline for a set of devices running the new implementation. And together they qualified respective bundles that we used to roll out in the production. With that, it concludes our second case study. And I'm going to hand it back to Krishna to talk us through the rest of the talk.
Thank you, Sri, for providing detailed insights on how we deploy massive brownfield deployment. As we all know, Meta deploys at scale. Let's go through some of the Fboss scale numbers. We have massive Fboss devices in the fleet that's being deployed, and it's been doubled every year. As Sri mentioned, we always do onboard upgrades in the fleet. This is because we want to cause minimal disruption to the hardware. The amount of time it takes is in the order of weeks, and we do several onboard upgrades over a year. The next three items capture about the vendors and the platforms. The number of vendors we have is 2, which is Broadcom and Cisco. As you can see, from these vendors, we have more than 5 ASICs, and also we have more than 10 platforms deployed across several layers from rack switch, fabric, spine, and aggregators. The last 2 rows captures the number of SDKs we got from the vendor. At any given point of time, we have 5 SDKs deployed actively in the fleet, and also we integrate more than 10 plus every year to our Fboss. I would like to capture some of the highlights to highlight on some of the methodologies we used and the outcome of it. Always deploy early and iterate so that you can deploy always early to the production and catch bugs early. Having a robust test suite in place helped us here. As you all saw, we had more than 1,000 plus test cases we reported to SAI. That helped us catch issues much more earlier, and also running it on the vendor side made us much more with a quicker iteration. Always set up a canary pipeline. This is because roll out your software and hardware to a subset of switches before deploying it to the fleet. As you all saw, open sourcing played a critical role for us while onboarding a silicon vendor. This is because vendor helped us running these test cases. So always be ready to open source. With this, we're able to achieve the following outcome. We're able to achieve massive scale deployment. We're able to achieve diversity across ASICs, across vendors, and across SDKs. We're able to make frequent updates to the production fleet. We're able to roll out several bug fixes and also enable more features to the fleet. And the last, we're able to onboard a new silicon vendor. We would like to thank the Fboss team and the partner teams at Meta. We'd also like to thank the ASIC vendors who were there with us from the beginning through the design all the way till the deployment. We'd also like to thank the SAI community who helped us design such a robust APIs for unifying our software. With that, I would like to conclude my talk. Thank you for joining us. Please reach out if you have more questions. Thank you.